and I recently created an Instagram account. You can follow me there as well. Next, we move on to the classification of signals. Now, as we said that we can classify systems into linear and non-linear systems. Similarly, we have classifications for our signals as well. Now, why is it important? It is important because out of these classifications, you will finally come across what are the characteristics that define a signal as a digital signal. Now, the first category of signals is the multi-channel and multi-dimensional signal. By now, you know that a signal is a function of one or more independent variables. Now, this function, which is the dependent variable or your signal, this can be real valued, complex valued, or vector. The examples of real valued and complex valued signals are shown. Now, vector signals, what are these? These are the signals that are generated by multiple sensors or sources. So, for example, if you have a signal coming from 3 sensors, how such a signal can be represented? It is as shown here. Now, such a signal that can be represented in the form of this vector is a multi-channel signal. However, all these 3 examples are of one-dimensional signal. So that means that the signal that we talked here as an example of a vector signal is one-dimensional multi-channel signal. So now let us talk about multi-dimensional signal. Now, if a signal can be represented as a function of m independent variables, it is a signal in m dimensions or an m-dimensional signal. As an example, we can consider the black and white TV picture, and the intensity or brightness versus time representation of a black and white TV signal can be this. Note that this signal is a function of three independent variables, and this is a 3-dimensional signal. Let us consider another example of a color TV picture. Since red, green and blue are the 3 principal colors, the combination of these colors form other colors. So this color TV signal can be represented in this vector form, that is it is coming from 3 channels or 3 sources. So it can be represented as a vector. Since each of the 3 signals can be represented as functions of 3 independent variables, these are 3-dimensional. So a signal from a color TV picture comprises of what we say a multi-dimensional and multi-channel signal. Next, we have continuous time and discrete time signals. Now, continuous time signals or analog signals are defined for each and every value of time. This means that these signals can be defined as functions of some continuous variables. So these are some of the examples of continuous time signals. Discrete time signals, on the other hand, are specified only at some specific values of time. Now, mind it, these time instants need not be equidistant, but for mathematical convenience, these are usually taken as equidistant. So this can be the example of a discrete time signal. It is to be noted here that I represented a discrete time signal as x is a function of some n, which is taking some discrete values, and depending upon the discrete values that n is taking, I am ultimately obtaining a discrete time signal. So as you can see that this is a discrete time signal which is obtained by selecting the values of the analog signal at discrete time instants. That is also called sampling, and it is this very term that I mentioned while I talked about analog to digital conversion. When I talked about the steps, the first step was sampling, and it is this sampling that is required to convert an analog signal to a digital signal. Third category is the continuous valued or discrete valued signals. Now, we talked about continuous time and discrete time signals. The representations xt and xn respectively are used to denote both the categories of signals. Now, these 2 signals can either be discrete valued or continuous valued. Now, the point to be noted here is that discrete time and continuous time signals, their classification was based on the values that abscissa is taking. Abscissa means the values the values that the independent variable is taking. Like if the independent variable of which that signal is a function, if it is taking continuous values, we call it continuous time signal, and if that independent variable was taking discrete values, the resultant signal was discrete time. Now this was the category that we talked about. Now next we are saying that these xt and xn can be continuous valued and discrete valued. Here we are talking about the values that will be obtained on the y-axis corresponding to these signals. Here we are talking about the y values that we will be obtaining. Earlier we were talking about the x values. This classification is based upon what are the values of the function itself. The continuous valued function can take continuous y values or discrete y values. Similarly, the discrete time function can take continuous or discrete y values. Now, if the signal takes all possible values on a finite or infinite range, we call it a continuous valued signal. However, if a signal takes values from a finite set of all possible values, it is a discrete valued signal. So this is how it looks like and what I'm talking about. Now concentrate on the y-axis. So this signal is taking some finite value on this y-axis. It is not covering each and every point on this y-axis. It is only selecting for such values. The signal is also discrete time because it is not taking continuous values of time. It is not taking all the possible values of time. And if we see the y-axis, it is also not taking continuous values over there as well. So this is an example of discrete time and discrete valued signal. And this is what we call a digital signal. So when somebody asks you what is a digital signal, that is, if a signal is discrete time as well as discrete valued, only then a signal is called a digital signal. So when we talk of digital signal processing, in order for the signal to be processed, it must be discrete in time and its values must be discrete. That is, it must be a digital signal. So that means if we have to process a signal by digital means, if we have an analog signal, first of all, it has to be sampled at finite instants of time. That means that an analog signal has to be sampled at discrete time instants, and the resulting signal that we will be obtaining is discrete in time values, the discrete time signal. Note that after sampling, the signal is not yet in a position to be called as a digital signal. It is only a discrete time signal because it has been sampled at discrete time instants, because it has been obtained by sampling the analog signal at discrete time instants. Is this point clear? Now the next thing is that some sort of a quantization has to be performed on this discrete time signal, and it is this process, this quantization process, which results in quantizing the values of this discrete time signal to some discrete values, to a set of discrete values. And after this quantization process, we will be getting a signal which is discrete time as well as discrete value. Now what is quantization? What is this process doing? So this is the process of converting a continuous valued signal to a discrete valued signal. Sampling was working this way, quantization is working this way. So quantization is basically an approximation process which can be obtained by truncation or rounding off process. So for example, if in a digital signal 0 to 15 values are allowed, like 0 to 15 integer values are allowed, and if your continuous valued signal is, for example, having a value of 8.58, then in the quantization process you will be employing the method of truncation, that is, you will be dropping the decimal places altogether or rounding off the value using significant figures. We say that we have quantized the continuous valued signal to integer values. Deterministic and random signals can be the last category of signals. Now before discussing that, I want to make a point clear that if at all you want to mathematically analyze a signal, it can be done only if the exact mathematical representation of that signal is possible. Only then the mathematical analysis and processing of the signal can be done. So, deterministic is something that can be determined. Its past, present and future values can be determined. And how this is possible? If there exists an explicit mathematical function or representation to describe such a signal. If there exists an explicit mathematical expression to define such a thing. So a signal is deterministic if its all past, present and future values can be known in advance, and that too without any uncertainty. However, if the signals evolve with time in an unpredictable manner, such signals are called random signals. That is, there exists no explicit there exists no explicit mathematical formula for such signals, and if at all any representation exists, it is too complicated to be of any practical use. So we use theory of probability or stochastic processes to determine such signals, to determine the outcome of such signals.